Hi there, welcome to another new video. At the end of this 12-minute video, I promise you, you will be able to understand and make a difference in your study and able to write easily in your exam. Let's begin. At first, let's find out what is countercurrent. In a U-shaped tube, suppose this is a U-shaped tube, when the flow is close to each other, parallel to each other, and counter to each other. So when the flow is close to each other, parallel to each other, and counter to each other, then it's called a countercurrent system. You know that osmolarity of interstitial fluid in almost all part of the body is about 300 milliosmol per liter. At hypothetical time 0, let's assume that loop of Henle and interstitial space is filled with the fluid of same concentration, that is 300 milliosmol per liter. That is also same as that fluid leaving the proximal tubule. Now let's draw the schematic loop of Henle. Inside the loop and the interstitial space all are 300 milliosmol per liter. Next, keep two things in mind, that the descending limb is highly permeable to water but impermeable to solute, and the ascending limb is strictly impermeable to water but permeable to solute. Now, most important thing in number 2 situation is the pump in thick ascending limb. What is the pump? Sodium, potassium, 2-chloride symporter. Now what this pump do when it becomes active? It tries to maintain 200 milliosmol per liter concentration gradient between tubular fluid and the interstitial space. This is very important. Remember, the pump will try to keep 200 milliosmol per liter concentration gradient. Let's draw the pump in thick ascending limb. This is the pump. This is the pump. This is the pump. Let's write descending limb. This will be same, 300, 300, 300 and 300. Now this pump will pump out solute, and as it is pumping out solute, so previously it was 300, now solute is going to interstitial space, so it will be 200 milliosmol per liter, and the interstitial space will be 400 milliosmol per liter. Now see, 200 milliosmol per liter gradient is established. Next, what happens is that interstitium got higher osmolarity than the tubule. You see, due to the solute reabsorption from the thick ascending limb. Now this hyperosmolar interstitium will draw fluid or water by osmosis from the descending limb, and the descending limb osmolarity will now become equal to the interstitium, that is 400. Got it? You can see as water is going out from the descending limb, the osmolarity is increased. So in number 3 situation, we have seen that water is out from descending limb and osmotic equilibrium is established between the interstitium and descending limb. Next, let's see when new fluid arrives from the proximal tubule to the descending limb. Now let's suppose these are the new fluid which comes from the proximal tubule to the loop. Then what happens? So this will enter the descending limb. These are the two new fluids. So this new fluid will push the previously present fluid through the U-tube. So now the situation will be like this. 400, 400, 400, 400, and the previously present 200, 200, and the rest 200 and 200 fluid will be getting out of the system. So these two will enter, these two will be pushed out. Let's write the osmolarity like this here: 400, next 400, but in upper portion write as 300 and 300. Why osmolarity is less written here? Because water comes out at the beginning portion of the loop from the newly added fluid from the proximal tubule. So that water actually dilutes these interstitial solutes. Get it? Remember to write these two values like this. Now notice that by adding the new fluid, the gradient between the thick ascending limb and the interstitium is lost. You know that 200 milliosmol per liter gradient is produced by the pump in thick ascending limb. You can clearly say that thick ascending limb 400, interstitium 400, 400, 400. So the gradient is lost in every species. So what happens? Next is the pump gets activated. You know, the pump will try to establish 200 milliosmol per liter gradient. So the pump will be now activated and it will actively pump out solute from the thick ascending limb to the interstitium. So in number 4 situation here we found that newly added fluid is there and gradient is lost. So in 5th step we draw the pump here. So the pump is active now and it will actively pump out solute from the tubule to interstitium. So here the osmolarity will be like this, 300, and in interstitium it will be 500, 300, 5, and here 150 and 350, 150, 350. Now see, in every space 200 milliosmolar per liter gradient is established by this pump in thick ascending limb. Now let's write the descending limb osmolarity. That will be same as previous, that is 300 here, 300, 400 and 400 here. So again 200 milliosmol per liter gradient is re-established. The main thing here is solute out. Previously in number 2 step we have also seen solute out. Now in step 6 you know what happens, it's like the step 3. So in step 6 water will come out osmotically and it will establish a osmotic equilibrium between the descending limb and the interstitium. At first write the interstitial osmolarity, then equilibrate. So in descending limb the osmolarity will be equal to the interstitium. So write this as 350, this will be 500 and this will be also 500. In ascending limb write same as previous, that is 300, 300, 150 and 150. So in step 6 water out from the descending limb. Here you can see, if you compare this interstitial osmolarity with the initial step, which was 300, now it has reached to 500. Okay, so the osmolarity is increased. These processes from step 4, 5, 6, these are actually repeated. Why? Because there is always adding of new fluid from the proximal tubule. So this step 4 to 6 is repeated. Now we get final osmolarity like this. At the tip about 1200, next 800, 500, 300, maintaining 200 milliosmolar gap. So we can write this as 1000, this as 600, this 300, and here 100. In the descending limb, it will be the same as interstitium as osmotic equilibrium is established. So this will be 1200, 800, 500, and 300. So in the final process, this step 7, we can get the osmolarity as high as 1200. You see, and osmolarity is gradually increasing in the deeper part of the loop of Henle. This multiplying process keeps adding sodium chloride in the medullary interstitium, and due to this multiplying property, this process is called countercurrent multiplier. Hope you have learned something new today in an easy way. Give us a like and subscribe to our channel. In the next video, we will discuss about countercurrent exchange system. Hope to see you soon. Till then, bye bye.